Hello, everybody, and welcome to this IEEE Computational Society webinar entitled Sustainable Futures in AI, Exploring Efficiency and Emerging Paradigms. I would like to send a warm welcome to Professor Claudio Gallicchio. He's smiling now because I've probably got his name pronounced wrong again after trying to practice. But he is an assistant professor at the Department of Computer Science at the University of Pisa, Italy. And his research is focused around deep learning, dynamical systems, and randomized neural systems. He is also the co-founder and chair of the IEEE Task Force on Randomization-based neural networks and learning systems, and also an associate editor of the IEEE Transactions on neural networks and learning systems. And without further ado, I am delighted to hand over to Claudio now for what is going to be an amazing talk. So over to you.
Thank you very much, Keely. I'm very glad to discuss today our efforts at the University of Pisa to create, let's say, a more sustainable future for the AI research. And in order to introduce, let's say, our more technical work, let me start by observing that the current path of deep learning research is largely unsustainable. And this is because often we probably we tend to focus only on the accuracy of our deep learning algorithms and deep learning models. But there is not only accuracy on the table, and we believe that the accuracy needs to be put in perspective also of the computational cost that is required by training in order to achieve that accuracy. And let me try to explain this point a little bit more in detail. So what we can see here is a plot of the compute that is required by training state-of-the-art AI algorithms on the vertical axis over time on the horizontal axis. And in particular, what you can see here is that the doubling time for the compute resources needed by training deep learning algorithm is around 3 months. This is very, very small amount of time, right? So the increase is really really large. As a reference here, I have indicated the doubling time that follows the Moore's law, right? The Moore's law tells us the way in which the computational resources are made available through conventional electronic systems. So this doubling time is around 2 years. And so we see that on the one end, we have a doubling time of 3 months for deep learning training. On the other end, we have like 2 years, and even more than that because of physical limitations of the Moore's law. And so there is like a big discrepancy between the resources that are required even more by our research community and what is available in physics and in electronic devices. So this is several impacts. And for example, there are environmental impacts in terms of pollution, as training a single AI model can emit as much carbon as 5 cars in their lifetime. So I think this is a very nice paper from 2019, where it has been analyzed how much is required in terms of, let's say, energy and carbon impact of training a large NLP pipeline and transformer pipeline. So it was found that actually there is very strong impact in terms of pollution and CO2 production, but also in terms of energy, like the energy needed for training just one of these systems. Even at that time, like 5 years ago, was like around 54 US households in 1 year, right? Just one training. Okay, and this continues to get worse and worse. Right now, we have GPT-4, like an instance of a very big and powerful deep learning algorithm, and this has the huge amount of 1.7 trillion of trainable parameters. We can just estimate the training costs, but we know that for training GPT-4, they've used like 25,000 of 800 GPUs for more than 90 days. Right? And so the cost of doing this training was like more than $100 million. And the amount of energy that was necessary in order to train GPT-4 is estimated to be between 50 and 60 thousands of megawatt. This is a gigantic quantity of energy. It's like more than 5 years of 1,000 average US households. This just for training. And we know that in this case, inference cost can even be more than training cost because we use these kind of technologies every day. And it is estimated that the inference cost for GPT-4 is, let's say, around per month is around the electricity of 26,000 US households, right? So there is a huge impact in terms of pollution, in terms of environment, in terms also of financial costs, right? Because there is a divide between those who can pay the bill of $100 million and those who can't, right? And overall, if we look at the climate, let's say, impact, we can see that while AI can be very useful to address some of the problems related to science, for example, or in general to advance the quality of life of humans all over the world, then AI also, on the other, let's say, side of the coin, risks to sensibly accelerate the climate crisis. And this is relevant, like we've seen under several perspectives, but also under political perspectives because of a number of agreements that are, let's say, legally binding the nations to follow specific paths, right? So we have, for example, Paris Agreement that focuses on limiting the temperature increase of 1.5 degrees above pre-industrial levels, which is a huge quantity. And also, for example, the European Green Deal, just to mention two of them, as the objective of make Europe climate neutral by 2050. So when we are developing our systems, our AI algorithms, we need to consider this in the perspective of the impact that this will have on our research, of course, but also on the future, right? On the future of the accessibility of the deep learning strategies, right? And so what can we do? Maybe we can, at a certain point, we can sit and observe the differences between what we can create right now as state-of-the-art artificial intelligence and what has been there since a lot of time, right? The natural intelligence, right? The brain. And we can see that, for example, if we consider our now large language models, they can have a compute that goes around 10 to the power of 15 flops. But the brain has even more than that, like 10 to the power of 22, it's estimated. On the other hand, the energy that you need to train a state-of-the-art AI system like GPT-4 can range between megawatts and gigawatts, so a huge amount of energy. And on the other hand, our physical, analog, and let's say natural brain consumes only 20 watts of energy, right? So like a bulb, light bulb. And instead of, let's say, needing like a gigantic quantity of energy, we just need like a coffee and a banana in order to do our tasks every day, right? So what I'm saying is that probably we need to also to start creating systems that perform incredibly well, like deep learning systems we are doing now, but also to start looking more at the way in which our brain processes information. So overall, what I want to say is that deep learning models achieved a tremendous success over the years. We know this very well, but this comes at a very high cost, right? High cost in terms of money, in terms of time, in terms of energy consumed, in terms of pollution, right? Also political costs. The point is that sometimes maybe we want to pay this cost, right? But do we really need to pay this cost all of the times? Right, so probably we don't need to pay this cost all of the times. And for example, in embedded application, we cannot even be able to start paying this cost, right? Because we want to probably create a distributed intelligence or a pervasive AI applications where the neural networks and the deep learning algorithms are running on top of very small devices. And on these very small devices, you cannot even run backpropagation. Or you can do that, but in a very slow way, right? So maybe putting in inference, use these systems like sensor devices wearable devices like smartwatches or phones, like in inference, right? That's possible. But if you want to do personalization on device, then it becomes progressively more complicated. So what can we do? We can broadly look at this area of research of deep learning, very broadly speaking, like a composition of two aspects: architectural biases and learning algorithm, the power of gradient-based learning algorithm. So by architectural biases, I mean the computational properties, the mathematical properties of the neural architectures, even if we don't consider, let's say, the learning algorithm. So what are the computational properties of the neural architectures? And what I'm trying to discuss today is a way in which we can probably try to avoid as much as possible the learning algorithms and try to leverage as much as possible the architectural biases. So let's see how far we can go if we focus only on that. And after all, our desirable properties for an AI system, given all the context from the previous slides, is that we are able to perform fast learning, so to quickly adapt to new data and tasks with minimal retraining, to have a very low training cost, which means that the training is economical in terms of computational resources needed and energy consumption, but also to be able to model dynamical information in an efficient way, right? So to handle temporal data and dynamical varying data in dynamical varying environments. And finally, to be able to, or to be amenable at least for hardware implementation. So to be suitable for deployment in a wide range of hardware platform, not only very big data centers or TPUs or GPUs enabled devices, but let's say also low powerful devices. Okay. Right, so I'm trying to introduce now a paradigm in neural networks that tries to address all of these aspects, and this is called reservoir computing. So I really suggest you to have a look at this book that has been edited by Kohei Nakajima and Ingo Fischer. It is a collection of, let's say, chapters and papers from the research area. And I would like at least to mention briefly one of my favorite quotes, which actually is from the front matter of the book by Herbert Jager, one of the pioneers in this research area, that tells that reservoir computing seems simple but is difficult, feels new but is old, open horizons, and is brutally limiting. And particularly, I would like to stress the feels new but is old, because even if these ideas of reservoir computing that I'm going to introduce in a moment, they root back to the late 90s or the early 2000s, as probably all the good ideas that are simple but effective, really effective in practice, keeps invented and reinvented every 2 or 3 years. So every now and then you can see in the top conferences a few papers that actually reinvent the ideas beyond reservoir computing. And so I think this, from the, let's say, from a positive way of thinking, this can be seen like a way to keep young this research field. All right, so I'm not going to dive into details. For that, you have the book. It is available for free online, but one thing at least I would like to introduce is the basic way in which we model neural networks for temporal data, for sequential data in particular of temporal nature, that is recurrent neural networks. So I'm going to, let's say, at least introduce very briefly the framework. So here we have on the left the basic organization of a vanilla recurrent neural network, where you have the input signal that varies over time in red. Then you have the recurrent hidden layer in green. This creates a latent representation of the input signal, and the output layer in blue, that or readout layer, that computes the output by combining the activation of the neurons in the recurrent layer. So in formulas, you have two equations basically that needs to be implemented by your neural network. The first one is the state transition function of the recurrent layer, and this involves the hidden latent state ht as a nonlinear function of the input signal. And on top of that, you have the readout layer that can be, for example, as simple as a linear combination of the neurons from the recurrent layer, as in this case. But this depends on the application that you want to use, right? So you can have a classifier for classification problems. But the point here is that all of the parameters in this non-linear transformation, or the linear transformation, for example, in the output part, they all need to be trained, right? And we know that training these kind of systems becomes equivalent to training a very deep forward neural network, right? And you need backpropagation through time in order to do so. This becomes progressively more difficult as the length of the time series become long. And there's a number of propagation issues like fading or exploding memory, which means that the latent representation can become unstable or unstable in the long run, meaning that a tiny perturbation in the input can explode in the internal representation of the network, or let's say differences in the inputs at different time steps can vanish over time, right? So this becomes more difficult to solve problems where you have very long range dependencies from the input to the expected output. And then you have also the infamous fading or exploding gradients, which is, I think, more famous and more widely known, where basically you have the same problem, but for the gradients that are propagated backwards from the, let's say, output layers back to the, let's say, different time steps of your unrolled recurrent neural network architecture. So how we try to address these ideas and these problems, right, in reservoir computing? We try to address this, I think, in a very elegant way by following this philosophy. That is, randomization is computationally cheaper than optimization, which is a quote from a strand of works by Rahimi and Dracht, and in this case from 2007 in IEEE. And this paper also won the Test of Time Award 10 years later, so 2017. It's the ideas beyond the random kitchen sinks kind of algorithms. But now we try to use this idea of randomization instead of optimization in this sense, right? So we want to use as much as possible the intrinsic computational capabilities of recurrent neural networks, what we can call the architectural biases of recurrent neural networks, even prior or in absence of learning of the recurrent connections, right? And so this is what we have as a first instance of reservoir computing model. It is called the echo-state network, and it was proposed by Herbert Jager and collaborators in the early 2000s. So in this case, you have a very similar architecture to the vanilla recurrent neural network. Essentially, the recurrent layer now is called the reservoir layer, and the output layer is the readout. So the equations can be the same as before, but the crucial point is that now the parameters of the state transition function, so the parameters of this green part in the architecture, now they are randomly initialized and left untrained. And only the parameters of the readout part, the readout layer, which is non-dynamical, are trainable, right? So the crucial thing is that the representation layer is fixed. The one that creates the latent representation of the input signal is fixed, and only the output layer is trainable, right? So there is a huge theory here behind this that we cannot dive into now, but let's say at least at the level of the intuition, how is this possible, right? Because now instead of looking at this recurrent hidden layer as a layer in a deep neural network, right, that we want to blindly train using backpropagation through time or any equivalent algorithm, now we look at this representation layer under the prism of dynamical system theory, right? So for now, for us now, this layer is no longer layer in a neural network, but it's like, in this case, an iterated map that evolves over discrete times. It's like input driven, it's nonlinear as a number of properties, right? And so when we focus on this layer as a dynamical system, we can put a number of constraints in order for this dynamical system to behave well under a number of aspects. And first of all, under stability perspective. So we, for example, we can focus on the weights in these matrices. For example, here I have highlighted the recurrent weight matrix that rules the recurrent part of the system. This can be random, but needs to determine stable dynamics in the long run, right? Because we don't want that the system explodes its memory over time. So in order to do that, there is, let's say, a very real vast literature, but the basic idea is that we can control the asymptotic stability by constraining the eigenvalues of this metric. So in practice, this boils down to this very simple condition. In theory, in the literature, this is called the echo state property, and I suggest to have a look if you want to dive into the mathematical aspects of this, into this very popular paper in the area that is called Revisiting the Echo State Property. But at least at the level of intuition, this is what happens, right? So on the left part of these slides, we have an example of a situation in which you have this asymptotic stability property in place. So you have a valid echo state network. On the right, you have an example of a situation in which you don't have this echo state property in place, so you don't have a valid echo state network. In practice, in this case, we are running the system following the same, or we are running the same reservoir on the same input, right? But at a certain point, we give a typo in the input, right? And the typo determines a perturbation in the reservoir state, right? So the HT. And the possible states in which your system is indicated, for example, by the different stars here, right? The red one, the blue one, and the green one, right? And after the typo, your system again receives the same input. So what happens after that? If the echo state property is in place, then again, your system will converge to a unique solution. In this case, it's, let's say, a trivial case, and everything will converge to the origin of the phase space. But let's say when you have a non-trivial input signal, this means that you will, in a sense, synchronize the possible latent representations if the input trajectory is the same to the same state trajectory. So in a sense, you are creating a consistent representation of your input signal. On the other hand, if you are in a situation in which the echo state property is not in place, then you have a situation like the one on the right part of the slide, where depending on the initial conditions, you can diverge to different solution of the dynamical system. So even, again, if you receive the same input, then your latent representation become, after a single typo, so different that it will destroy the generalization capabilities of your system. So basically, you want to constrain the eigenvalues of the Jacobian of your reservoir to be smaller than 1, and then you will be in the situation on the left part of this slide. Okay. As you may guess, if you avoid learning completely in the dynamical part of your recurrent neural network, you have a number of advantages, all right? So first of all, you have a clean mathematical analysis that can be done and then can inform even learning algorithms, right? Because you can create a better architecture that has a better, let's say, computational property, and then can even, after that, be trained end-to-end. But even if you don't do that, you have a system that works well in applications that is strikingly more efficient than fully trainable systems, right? Because you don't need to apply backpropagation through time to an entire part of your architecture. And then you also have advantages in terms of hardware implementation. So as we have little time, I would like at least to focus on a few of these points, starting from the efficiency part. And for this, I would like to make an example it is related to, in this case, a classification problem. So here I have selected to illustrate this concept, a classification problem that is paradigmatic example of this concept. So in green, you can see the accuracy that can be achieved by a reservoir computing system. In gray, you can see the performance that can be achieved by a similarly sized, fully trainable recurrent neural network. That is like a selection among gated recurrent units, antisymmetric recurrent neural networks, and other state-of-the-art systems. So you can see the accuracy of the reservoir computing system in this case is similar to the accuracy that can be achieved by the fully trainable system, but you're losing like something like 4 percentage points in terms of accuracy. So you're 0.04 accuracy lower than the fully trainable system. But the striking aspect is that as you don't have to do the learning in the recurrent part of the system, you can train the same system with a striking advantage in terms of time, like 2000 times faster, or also in terms of energy that is consumed in order to reach this 0.93 accuracy on the task, like with an advantage around 1700 times in terms of energy consumption with respect to fully trainable systems. And this efficiency can be exploited in order to deploy these systems even on very, very small devices, like we have done in the past years in one of our previous projects that was called Rubicon. In this case, we have implemented these reservoir computing neural networks in very small sensor devices called TNNLS devices, where you have neural learning in 8 kilobytes of memory in total, plus development over the air. And this could be used, for example, in order to solve problems, let's say in complicated environments like hospital environments. Let me see if I can run the video. Okay, so what you can see here is the sensor here on top of this hospital robot. And this sensor is running the EcoStack network algorithm, right? So both the inference and the training. And in the environment around this robot, you have a hospital, and in this hospital, you have a number of other beacon sensors that are exchanging information with the sensor on top of the robot. So basically, they are exchanging packets of information, and they are evaluating the received signal strength, right? So in doing this, in the interaction between the robot, the humans, the environments, you have a trace of information like signals that are analyzed and, let's say, used by the sensor on top of the robot. And this, in practice, is done to localize the robot in the hospital, right? So in this case, the robot has the goal to deliver food and other goods to the different parts of the hospital, and we could achieve a very good accuracy in the localization, which means that you can deploy this kind of solution based on reservoir computing enhanced machine learning in environments, let's say, with a very tiny fraction of the cost that would require a very complicated localization system for robots using, let's say, magnetic devices. And another interesting aspect is related to the hardware implementation. In particular, hardware implementation in unconventional systems, not just, let's say, conventional CMOS-based hardware or electronic hardware. The basic idea here is that I have described so far, let's say, a system that can be implemented in software, right? So very easily, you can write a program in Python, or you can use one of our libraries in Python that, let's say, process the information, creates the reservoir, the different parts of the architecture, they do the training, etc., right? So in particular, you have a part of the program that performs the computations required by this reservoir layer. And essentially, what this is doing is like performing the computation of a dynamical system that so is, let's say, input-driven dynamical system, non-linear dynamical system with at least a fading memory over the input signals. And actually, what happens if you replace your Python program with a physical substrate? But well, you have exactly the same situation, right? So you can substitute your Python program for the reservoir with a physical substrate that can be, for example, based on memory stores or quantum systems or spintronics or photonics or even FPGAs that are, let's say, implementing the same concept of, let's say, input-driven dynamics with nonlinear behavior. And if you are able to observe these quantities in these, let's say, physical devices, then you can record the latent space in the reservoir that is created by these devices, like the memory stores, and then you can use these to feed the readout. So basically what I'm saying is that you can use the physical laws to do the computation instead of the GPUs or the CPUs, right? So you can use photons for doing the computations, even in passive photonic systems. And this has a very big impact in terms of energy consumption, right? And apart from these neuromorphic hardware implementations, you can even use what is called morphological implementations of this concept, where the reservoir computation is not performed by, let's say, an engineered systems, but is performed by, let's say, even like the skin of a soft robot, like potentially even by the skin of, let's say, an animal or, let's say, a human being. But the point is that actually you can use pressure sensors to monitor the different points of the, for example, of a robotic arm that is moving, for example, in this case, in a bucket of water. And you can encode the input using a motor that is on top of the arm in order to, let's say, encode by the movement of this motor the input signals that you want to give into your reservoir. And then by monitoring the, let's say, pressure on the different parts of the skin, then you have a non-linear dynamical response to the input that is being encoded on top of this system, right? So this is the kind of strange approach to computation, but it's a very good way, I think, to observe that actually everything in the physical world can be used for doing computation in a cheap way, right? This is, let's say, this idea of morphological computation has been pioneered by Kohei Nakajima and Helmut Hauser a few years ago, and actually has been demonstrated in physical systems. And for example, here, you can see an example in which these soft robot are misused in order to solve nonlinear tasks of a unidimensional time series, right? So kind of strange but super interesting way to solve problems on sequential data. Okay. More recently, these ideas of reservoirs and in particular generalization of this concept that we have introduced in the literature that is called graph reservoir computing. That is, let's say, generalization for processing data in the form of graphs. Has been implemented in hardware, in this case, in resistive memory arrays, in a recent paper that we have published on Nature Machine Intelligence. And what we found in this case is that it is possible to achieve state-of-the-art performance on the benchmark tasks for graph classification with an improvement in the energy efficiency in terms of, in this case, 40 times. All right. In this case, we have seen a number of, until now, we've seen a number of, let's say, way in which you can use dynamical systems to do computation. And in particular, let's say, in order to create systems that can learn effectively to map the input signal into a desirable target. One limitation of reservoir computing systems as they are now is related to the fact that in order to create a stable representation of the input signal, they need to have what is called a fading memory, right? This has been, let's say, briefly illustrated in one of the previous slides where I showed you the echo state property. But the point is that if I want my system to be contractive in a sense, because I want it to be stable, then progressively I will tend to forget the information that I gave to my system. And a recent development in this direction that I am performing here with my collaborators at the University of Pisa is trying to avoid these limitations of fading memory systems. So we are, let's say, studying what we call non-dissipative reservoir computing, where we create our reservoirs from a radically different perspective. So instead of constraining, say, discrete time systems, we start from the ODE formulation, so from the continuous time formulation. Then what we do, we want to impose, let's say, a non-dissipative, stable, dynamical behavior to our system. So in this case, for example, we have our ODE represented in this way. We want to impose a non-dissipative constraint, and the control theory tells us that we can use, in order to do so in a very simple way, in an architectural way, we can use antisymmetric recurrent weight matrix WH. If we do so, then we know that the Jacobian of this transformation will have imaginary eigenvalues, which means that the behavior of this system will be by design at the edge of stability. So it will be very rich. Okay, so we start from the ODE. We impose this antisymmetric recurrent weight matrix in order to enforce such critical dynamics, and then we discretize in order to have our, let's say, recurrent layer that we can, let's say, implement, for example, in software. And then if we discretize using the forward Euler method, then we have what we call the Euler state network, which has this modification of the state transition function compared to the conventional echo-step network, and where we have a number of hyperparameters like the step size of integration and the diffusion for stability of the numerical methods, but also we have this matrix here that is automatically, because of its construction, is automatically antisymmetric, right? So we can leave untrained all the weights, and the dynamics are arbitrarily close to the edge of stability. What does it mean? It means that you can process the information, you can latch long-range dependencies in the latent reservoir state representations by design without learning this property in your system. This, in application, has a very big impact because it reaches the more or less same accuracy of fully trainable systems and much better accuracy than conventional reservoir computing systems, but it is extremely more efficient, around 2,000 times faster and cheaper than fully trainable systems. And finally, as a technical aspect, I would like to mention at least briefly this idea of generating reservoir systems that are better than just random reservoirs, right? So until now we said we want to create a system that is like a random dynamical system under specific constraints, but maybe we can find a better reservoir than just a random reservoir, right? There are a number of ways in which we can create a better reservoir than just a random one, and I would like to mention at least one of these ways. This is intrinsic plasticity, which is a different kind of plasticity than synaptic plasticity. It's a plasticity that is related to the way in which neurons in the brains react to the same inputs, right? They can have different nonlinear behaviors, right? So the idea, rather than the change in the connection between the two presynaptic and postsynaptic neurons, right? Anyway, intrinsic plasticity works by adapting the gain and the bias of the activation functions of the neurons in the reservoir and tune the probability density of the reservoir neurons to max entropy distribution. What does it mean? It means that we just change 2 parameters per neuron, which are the gain and the bias, typically using Kalbach-Leblé divergence minimization. Starts with the distribution that is given by your reservoir, randomly initialized, and targets the max entropy distribution given the nonlinearity that you're using. And for example, for hyperbolic tangent recurrent neural networks, this is a simple Gaussian distribution. So you can find out very simple local learning rules that are alternative to backpropagation that are based on a couple of very straightforward hyperparameters, and that tell you how you need to change the values of the bias and the gain in order to maximize the entropy of your reservoir. Okay, so if you maximize the entropy of your reservoir, then you are putting your reservoir in a very excitable condition in which there is a very good transfer of information from the input signal to the dynamics of the latent reservoir space. And this can be suitably combined also with Hebbian and anti-Hebbian kinds of learning in this paper like shown in this paper by Miguel Soriano and collaborators. All right, using these ideas of reservoir computing and intrinsic plasticity, it is even possible to extend the advantages of reservoir computing to pervasive AI scenarios where you have both federated and continual situations, right? So we start from left to right, from centralized settings where all the data is available in advance on a single machine. Think like, for example, of human monitoring problems, right? So you have a number of users and let's say a number of recordings from the different users, for example, from wearables from the different users over time, right? You can have all of them in a centralized setting or in a federated scenario where every user, every client has its own data set all together, right? Or you can have a continual scenario where single machine gets all the data from clients in a streaming fashion, or you can have actually what's happening in the real world, right? So federated and continual scenario where every client has its own private data stream, right? So different users and different, let's say, experiences over time. And it's possible to use, in this case, reservoir computing to enhance these systems, the pervasive AI systems, in order to allow personalization in the local devices and at the global level, using, for example, exact federated learning at the level of the readout by aggregating the different components at the level of the readout, and using an extension that we have introduced last year in the literature for continual and federated intrinsic plasticity to adapt the dynamics in the different clients over time in a way that ensures the federated possibility of, let's say, aggregation of the dynamics, not only of the output functions, in a continual way. And you can use these ideas in real applications like autonomous driving applications. And this is an example from another project, European project called Teaching, that we have run in the last years, in which we have demonstrated cyber physical systems of systems application empowered by these continual and federated reservoir computing systems to personalize the experience of a human driving a car, where the driving profile is automatically modified by a reinforcement learning algorithm. And another component of the system based on reservoir computing is sensing the some physiological data from the human and is evaluating the level of stress and comfort of the driver. So there is like a sort of human in the loop here, because the human is, let's say, driving the way in which the cyber physical system is responding to its own commands. In the latest months, we are working with similar concepts of reservoir computing-based systems in a number of projects, and I would like to mention at least these two. One is Emerge, which is a Pathfinder project funded by EU, where we use neural and physical computing with reservoirs. Here we are creating what we call the archetype computing system engine that is based on dynamical systems seen like reservoirs, and minimal entities created by very small parts of robots that talk to each other, or let's say swarm or very minimal robots that talk to each other, and that create, let's say, by the aggregation of these very minimal dynamical systems, the awareness of, let's say, an aggregated dynamical system at a different scale that is able to solve a robotic problem in a better way. And the other project that I would like to mention is Neurone, which I'm running here at University of Pisa, and this is based on extremely efficient neuromorphic reservoir computing in nanowire network hardware, where we are using advanced reservoir computing technologies like ordered networks, residual reservoir computing, and state-space models based on reservoir computing with nanowire network memory-stable hardware to deliver ultra-efficient learning. Well, to summarize a few key concepts from my talk today, I try to convince you how reservoir computing is a principled approach to sustainable AI, so in order to devise training efficient sequence models. And the basic idea is that the dynamics in the recurrent neural network, or in a neural network in general, can be constrained in a smart way, in a mathematically grounded way, in order to offer useful architectural biases. So to perform well, even in the absence of training in most of the connections in the network. And this has a great potential in pervasive AI scenarios, as we have demonstrated in recent years, where you have reduced computational resources available, and even in neuromorphic hardware. And even beyond that, when you have your systems, your new reservoir computing architectures, like, for example, ordered networks, based on that, you can create smarter neural architecture, even training them end-to-end, because if you have a flow of information that is optimized, also the flow of gradients will be optimized. And following this line of research in our group, we have extended this idea to cope with problems in dynamically evolving graph networks in deep learning for graphs. So in this case, even if the system is no longer a dynamical system, then you can see like the dynamical process in the evaluation, let's say, from the input graph to the latent representation like an ODE, and then you can apply similar strategies that we have introduced in the field of reservoir computing, even if you train end-to-end, right? So you can stack a very large amount of layers that you can train in an effective way in this case. And globally, overall, I believe that reservoir computing and the contributions of reservoir computing to the field of deep learning can be to create a greener path for the AI development without the need of extensive parameter training. Before leaving, I would like to mention a few online available resources that you can find and you can try for your own research. First of all, code, because code rules the world. And I would like to suggest you a few repositories. And the first one is this one, Reservoir Pi, which is a Python framework for reservoir computing systems, where you can find a lot of reservoir computing primitives already implemented in NumPy. And I also suggest you a couple of, let's say, repositories from my GitHub. The first one is Deep Ecosystem Networks, and the other one is the one that implements the recent ordered networks. But also from our European projects teaching, I can suggest the AI toolkit. So if you want to create pervasive AI systems that are, let's say, empowered by these reservoir computing concepts, then you can have a look at our teaching AI toolkit. Let's say it's a microservice-based system that uses reservoir computing for sequence learning. Then, as of course, today it was not possible to touch every aspect of reservoir computing. I would like at least to mention that if you get interested in these topics, that maybe you can be interested in having a look. You can have a look at the tutorial that I gave in IGCNN 2021. Tutorial on reservoir computing. It's available on YouTube. Or if you're going to attend next WCCI IGCNN 2024 next month in Japan, in Yokohama, then you can attend our special session on reservoir computing with the new advances in methods, applications, and implementations. And finally, I would like to mention a couple of task forces. One has been also mentioned at the beginning of the talk. The first one is Task Force on Reservoir Computing that I co-founded a few years ago. And the second one is the Task Force on Randomization-based Neural Networks and Learning System that now is chaired by me. So this is all from me today, and I would like to stress that collaborations are welcome. So I invite you, if you are interested in these topics, if you want to know more on these subjects, or if you want to get in touch, feel free to send me an email or to get in touch by LinkedIn or Twitter. Thank you very much.
Well, thank you. I would love to give you a round of applause, but it's only me off mic. So thank you very, very much for an amazing session there. Can I ask people to type any questions they have into the chat or the question tab at the moment? And while those are starting to come in, really, really interesting. Can I ask you a question? Looking at the explainability side of reservoir computing, what are your thoughts about that? Because we all know the issues associated with deep learning.
Oh yeah, this is a very interesting question, a very good question. Explainability of reservoirs, it's like a topic that has not been analyzed too much in the literature. We are now performing some experiments with explainable AI. In Pisa, we are also skilled with explainable AI systems and research. Well, actually, there are a few insights from the aspects of explainability. First of all, you can create a distinction between systems that give you a memorization, a long-term memorization over the input, and then focus on specific aspects of the input, like specific frequency of the input domains, and systems that focus more on, let's say, a nonlinear transformation of the input signals, right? Mm-hmm. Again, in specific ranges of the input. So this can be useful, for instance, when you want to predict, for example, the next, let's say, the future behavior of a temporal model, for example, for financial systems or for clinical systems. But the other aspects that I find interesting is that you can use explainability in order to, in a sense, improve the way in which you use reservoirs. So instead of, let's say, looking the explainability alone of the system, you can use the outcome, for example, of SHAP in order to give a proper attention to specific time steps over time. So you can use conventional explainable AI techniques in order to understand in which part of your system, let's say which part of the input signal you need to attend to in order to better solve your problem. And we are creating sort of explainable AI enhanced attention layers to build on top of reservoirs to have, let's say, this efficiency, but with, let's say, more efficacy on a number of problems.
Thank you. That was a really good answer. As you said, it's kind of another emerging area that you're working on. But there is now a question. I don't know whether you can see that or you'd like me to read it out.
Oh, well, actually, I cannot see maybe in the system, so it would be nice to hear that.
Okay. So the question is, what about applying quantum computing?
Oh yeah. Quantum computing is another area of, let's say, physics-inspired research that is using reservoir computing as a, let's say, as a neural network tool. So both photonics and quantum computing now are, let's say, two driving forces in this, in a sense, neuromorphic area of research. And there are a number of research groups that are trying to use quantum computing in order to solve learning problems. Yeah, the point here is that in the reservoirs, at least in the basic fundamental versions, they are not trained over time, right? You can do some form of learning, but in the most simple approach that still is working well, you don't touch the reservoir part. And so as it is, let's say, easy to create a photonic or a quantum, it's easy, not so much, but it's possible to create these kind of physical systems that responds to the input in a fixed way, right? Without any learning taking place there, then this concept of reservoir computing are really making a lot of sense in this area, also in quantum computing. So I expect nowadays we are having the creation of photonic chips that are using reservoir computing as a core machine learning asset. Still, I don't see, let's say, full demonstration of reservoir computing in quantum devices, but I know that there is a lot of research nowadays in this field. So I can expect in the next few years to have some breakthrough here.
Wow, thank you very much. Well, I've just put a final call out in the chat for any more questions that people have. I think we are not getting any more. So I just want to say sorry for the sirens. I live close to the city centre. Well, I'm in work. And I think what you did was give everybody a lot to actually think about. So what I would like to do, given there's no more questions, I would just like to say, if you are coming to Wiki this year, this is a special session that you shouldn't actually miss. And you should also try and connect with Claudio on LinkedIn and have a look at some of those projects. I want to say that Teach one is very, very interesting for me. So I will definitely be having a look at that. Okay, so there are no more questions. So you have a few minutes. Oh, no, one has come in. One has come in. Okay, last one. The question is, well, it's not a question, it's a statement. I find in my research that small world topology is very good to initialize the reservoir weights. That's, I think it's just a comment there. For Breba.
Yeah. There is a lot of research in this area. So couldn't have time to touch these aspects, but what was mentioned in the chart is actually true. As let's say an interesting perspective in which we can create better reservoirs is to create patterns of connectivity between the neurons that determines very good properties in the dynamical processing of the information, right? One of the strikingly and surprisingly good is the of such examples is the ring topology, where the neurons are connected in a ring. This is a very simple one, but it's a very effective one because it creates an orthogonal recurrent neural network in practice, right? It's a very simple strategy for that. But another one is the small world topology. So small world topology is very good, and also it's linked to the properties in which some parts of the cortical areas in the brain are connected. So it's a lot motivated also by the biological observations. And these pointed out in the chart is one of the most active area of research, because when you want to create a fixed topology that you cannot change over time because you don't want to learn that part, then using one that has a good property is key. And so, for example, using small world topology is a strong way of creating your reservoir. So I support these ideas, and thanks for pointing out in the chat.
Okay, thank you very, very much for answering those questions. Thank you to the participants, for Joellen, who is in the background, who has been here. And thank you, Claudio, for an interesting talk. And hopefully we will meet at Wiki, along with many of the participants in this call. So thank you very, very much.
Thank you very much for the opportunity, and waiting for see all of you in Wiki later this year.
Okay, thank you very much.
Thank you.